So to train a modern foundation AI, you need, well, you basically need a warehouse full of specialized silicon.
Oh, yeah, and 12 straight days of maximum compute.
Right, and like $2 million just to pay the electricity bill. It's an industrial scale operation.
It really is.
And honestly, it feels entirely disconnected from a solo developer, just typing away on a laptop.
Completely disconnected, yeah.
But today, we're going to show you how that lone developer can actually take that exact same billion-dollar cloud-based brain, aggressively compress its neural pathways, and run it locally on something as mundane as a smart microwave.
A microwave, a TV remote, you name it.
Welcome to the deep dive. We are tearing open the black box of large language models to look at the actual engine underneath.
And it's the most necessary transition we can make right now, moving away from this cultural perception of AI as a magical, all-knowing oracle and seeing it for what it truly is.
Which is just math, right?
Exactly. It's applied calculus and engineering. Because when you see the underlying math, the illusion of magic vanishes, but the potential for what you can actually build just explodes.
I love that.
We are going to break down the highly technical mechanics of how these models are forged, how we mathematically compress them without lobotomizing them.
Which is key.
Right, and how you can deploy them locally to augment human intelligence rather than replace it.
And we know why you're tuning into this deep dive. You're not here for a surface-level summary of the tech news.
No, you want the mechanics.
Exactly. You want to know how this technology can empower you, the individual, to build something resilient and useful. We hear this constant narrative of AI existing just to crush human grandmasters at chess.
Or automate away our creativity.
Yeah, exactly. So today, we are focusing on the architecture of collaboration, building localized, specialized AI that acts as a cognitive exoskeleton.
I like that phrase, a cognitive exoskeleton. So let's start at the absolute bottom of the stack, the blueprint of the foundation models themselves.
Let's do it.
We throw the acronym LLM around constantly, right? But what actually qualifies a model as large in a mechanical sense? It comes down to three massive pillars.
Okay, lay them on me.
Parameters, hardware clusters, and the data ocean.
Right, let's break those down, starting with parameters, because that's the number everyone obsessively tracks online.
Oh, absolutely.
When we talk about parameters, we are talking about the internal variables, right? The specific weights and biases that the model optimizes during its training loop.
That's right. If you visualize a neural network as a vast, tangled web of connections, the parameters are the numerical strength of those individual connections.
And the scale of this has just exploded recently.
Oh, it's wild. A few years ago, a model with 1 billion parameters was considered massive. Today, we are dealing with state-of-the-art architectures operating in the hundreds of billions.
Or even utilizing a mixture of experts architectures pushing into the trillions. Right?
Exactly. And to optimize 1 trillion individual floating point numbers simultaneously, you have to move way beyond standard computing clusters.
You can't just use a really nice gaming PC.
Not even close. You require tens of thousands of specialized chips, like high-end GPUs or TPUs.
And you have to orchestrate them across massive data centers using complex tensor parallelism.
Yeah, just to keep the training loop from crashing due to memory bottlenecks.
Right, because you can't just fit a 70 billion parameter model on a single motherboard. You are actually splitting the neural network itself across different physical chips.
You have to.
But let's look at the engine that actually makes use of all that silicon. The architecture holding this all together is the transformer.
The famous transformer.
Yeah. Before 2017, the field relied heavily on recurrent neural networks, or RNNs, and long short-term memory networks. What was the mechanical bottleneck in an RNN that the transformer actually solved?
It was a fundamental limitation of sequence and time. An RNN processes data sequentially.
Meaning one word at a time.
Exactly. It ingests the first word, updates its hidden state, then moves to the second word, updates again, and so on. The computation for token number 100 physically cannot begin until the computation for token 99 is finished.
Oh, wow. Which means it's mathematically impossible to run in parallel.
Exactly. You can throw 10,000 GPUs at an RNN, and it doesn't matter.
Because GPU number 2 is just sitting there, twiddling its thumbs, waiting for GPU number 1 to finish reading the first word.
Precisely. And beyond the hardware bottleneck, RNNs suffer from the vanishing gradient problem.
What's that?
Well, by the time an RNN reaches the end of a long paragraph, The mathematical influence of the first sentence has been diluted so heavily by all those sequential updates.
So it forgets.
Yeah, the model essentially forgets the earlier context. If you have a pronoun at the end of a page, an RNN really struggles to map it back to the proper noun at the beginning.
Enter the transformer architecture.
Right.
And the beating heart of the transformer is the self-attention mechanism. This is where the magic happens. Well, it's not magic, it's matrix multiplication.
Just lots of math.
Right. Walk us through how self-attention actually works under the hood, because it completely eliminates that sequential bottleneck.
It really does. So self-attention allows the network to process the entire input block simultaneously. Let's look at the mechanics.
Okay.
When a sequence of text enters a transformer block, every single token is converted into 3 distinct vectors: a query vector, a key vector, and a value vector.
That sounds like a database retrieval system.
You can think of it exactly like that.
Okay, let's use a concrete example to ground this for you listening. Let's say the sentence is, the dog barked at the mailman because he was aggressive. The model needs to figure out who he refers to, the dog or the mailman.
That is a perfect example. So when the model processes the word he, the query vector for he essentially asks the network, I'm a pronoun, what noun in this sequence should I attach myself to?
Like it's literally querying the rest of the sentence.
Yes. Meanwhile, every other word in the sentence has broadcasted its key vector, which acts like a label describing what it is.
Okay.
Then the model computes the dot product, which is just a mathematical measure of similarity between the query vector of he and the key vectors of dog and mailman.
And because of the context it learned during training, the dot product between he and dog will yield a much higher numerical score than he and mailman in the context of barking.
Exactly. That score is the attention weight.
Got it.
The model then takes the value vector of the word dog, which contains the actual semantic meaning of the word, multiplies it by that high attention weight, and adds it to the embedding of the word he.
Wait, so mathematically, the representation of the word he is physically altered in the high-dimensional space to absorb the meaning of dog.
Yes, exactly. It establishes these long-range dependencies instantly across the entire sequence in parallel. Every word looks at every other word all at once.
And because it's highly parallel, you can split those matrix multiplications across thousands of chips seamlessly. That is brilliant.
It's the key to the whole scaling thing.
Now, what is the actual goal of all this math? During the pre-training phase, what is the model trying to achieve? The technical term is autoregressive next token prediction.
Which sounds incredibly dense.
Yeah, but it basically boils down to something wildly simple.
Right. It is the ultimate game of statistical autocomplete. The model is simply calculating the mathematical probability distribution for the next token in a sequence.
And let's clarify tokens for a second, because a token isn't a word.
Right. It's closer to a syllable or a morphological root. Like the word unbelievable might be split into unbelieve and able.
Oh, I see. Using algorithms like by-pair encoding.
Yes, exactly. So the model takes the sequence of tokens it has seen so far, passes them through dozens of layers of self-attention blocks, and outputs a massive probability vector across its entire vocabulary.
And that vocabulary might be 50,000 or 100,000 tokens long.
Right. It assigns a percentage to every single possible next token. It might calculate that the next token is 85% likely to be apple, 10% likely to be orange, and 0.001% likely to be tractor.
You know, that is the part that always gives me pause. This profound perceived intelligence. Its ability to write essays, debug servers, format data.
It all fundamentally reduces to guessing the next fragment of a word.
Yeah, but to make that guessing game sophisticated, the model requires the third pillar, which is the data ocean.
The massive data sets.
Yeah, where is this data actually coming from?
It's essentially a massive indiscriminate vacuuming of humanity's digital footprint. We are talking about data sets like Common Qual.
Which is just a petabyte scale scrape of the internet, right?
Pretty much. It takes snapshots of billions of web pages, forums, and blogs. Then you have highly curated subsets. A great example is the Pile.
I've heard of that one.
Yeah, it's an 825 gigabyte data set that specifically targets high-quality information. PubMed Central for medical texts, Arica for dense academic and mathematical papers.
Project Gutenberg for classic literature.
Right, free law for legal documents. And newer open corpora like Llama pushed the scale even further, reaching 3 trillion tokens.
So they basically dumped the internet into a blender.
Pretty much.
But I noticed a very specific anomaly when looking at the composition of these data sets. They aren't just natural human language.
No, they are not.
They are heavily weighted with programming languages.
Right.
We are talking about massive repositories scraped from GitHub, millions of lines of Python, C++, Rust, JavaScript.
Yes.
Why inject so much code into a model that is primarily built to generate human text?
That anomaly actually resulted in one of the most significant breakthroughs in the field of deep learning.
Really? How so?
Well, natural language is messy. English is filled with idioms, contradictions, sarcasm, and really ambiguous grammar.
Oh, sure.
If you only train a model on human language, it learns to mimic our speech, but it struggles with rigorous logic. Programming languages, however, are the exact opposite.
They are deterministic.
Exactly. They have absolute syntax. They are built entirely on conditional logic, if this, then that, else this.
They force a structural hierarchy. I mean, a Python script is essentially a directed acyclic graph of logic.
Yes. And researchers discovered that by forcing the model to predict the next token in millions of Python scripts, the model couldn't just rely on statistical frequency.
Right, because to predict the next line of code, the model actually has to track a state of variables.
It has to understand the step-by-step algorithmic flow. This strict syntactic data implicitly teaches the neural network how to break complex multi-step problems down into sequential logic.
So the logic actually bleeds over. By teaching it Python, you are inherently making it better at reasoning through a medical diagnosis or a legal argument, even though those have nothing to do with coding.
Exactly. The underlying structures of logic are universal. It's analogous to learning formal logic or higher mathematics. The cognitive framework transfers over to other domains.
That's incredible.
Yeah, models trained heavily on code demonstrate drastically higher scores on general reasoning benchmarks.
Okay, I have to push back here, because this is sort of the philosophical crux of the whole technology.
Okay, let's hear it.
If the model is just doing algorithmic autocomplete, if it's just minimizing a loss function by predicting the next token based on internet text and Python code, how do we suddenly get these emergent abilities?
It's a great question.
Like, how does making the parameter count bigger suddenly allow an autocomplete engine to deduce the solution to a novel logic puzzle it has never seen before?
It is the most counterintuitive part of the architecture, but it comes down to the empirical scaling laws.
Scaling laws, okay.
Research shows a strict mathematical power law between the size of the model, the amount of compute used, and the volume of training data. As you scale up the parameters and the data simultaneously, something profound happens to the internal geometry of the model.
Mechanically, what's happening?
Think about it this way. Memorizing the exact sequence of 3 trillion tokens is actually highly inefficient. The model's loss function forces it to find the most computationally efficient way to predict the next word. And the most efficient way to predict the outcome of a physics equation is not to memorize every physics book ever written. The most efficient way is to actually learn the underlying rules of physics.
To build an internal model of the world.
Yes. The network generates highly specialized internal representations. Deep within the hidden layers, specific clusters of parameters begin to act as specialized experts.
So one cluster might activate specifically for spatial reasoning.
And another for chronological timelines. It maps the conceptual structures behind the language. That is when you see emergent abilities switch on. The scale forces the comprehension.
That is absolutely fascinating, but it also presents a massive wall.
The cost.
Yeah. If it takes millions of dollars in compute, 6,000 specialized chips, and 3 trillion tokens just to force those internal representations to emerge, then we were talking about a permanent monopoly.
Pre-training, yes.
I mean, I tried to run an uncompressed 70 billion parameter model on my high-end laptop once, and it completely hard crashed my system in about 4 seconds.
Well, of course it did.
I ran out of memory before it even loaded the weights. So if I'm a solo developer, am I just permanently locked out? How do we bridge the gap between a billionaire's data center and my workstation?
This is where the engineering becomes beautifully subversive. You bridge that gap through the open source ecosystem and parameter-efficient post-training manipulation.
Okay.
You don't build the foundation yourself, you leverage what has already been built.
Let's talk about the democratization toolkit then. Where does the developer even start?
It begins with the software orchestration layers. Frameworks like PyTorch and JX handle the immense complexity of the tensor calculus in the background.
So developers can interact with these models using highly abstracted readable code.
Exactly. And then you have distribution libraries like DeepSpeed, which cleverly shard the model's memory footprint so you can optimize whatever hardware you actually have.
But the real keystone here is the Hugging Face Hub, right?
Oh, without a doubt.
It essentially acts as the GitHub for machine learning. Instead of dropping $2 million on AWS compute to train a model from scratch, you just go to Hugging Face and download the pre-trained weights for powerful open weights models.
You pull down Llama from Meta or Mistral or Falcon.
The billionaires pay the electric bill. You just download the result.
But there is a crucial catch. When you download that base foundation model, you are downloading a raw text continuator. It has vastly deep knowledge, but it has no behavioral guardrails.
Meaning what, exactly?
If you prompt a base pre-trained model with, what is the capital of France? It might output, what is the capital of Germany? What is the capital of Italy?
Because it just thinks you were writing a quiz.
Right?
It doesn't know it's supposed to be answering you. It hasn't learned the assistant persona.
Exactly. To mold that raw intellect into a useful tool, you have to transition from pre-training to fine-tuning. You need to provide the model with highly structured examples of how to behave.
Like thousands of prompt and response pairs that teach it to follow instructions.
Or to output data strictly in JSON format, or to speak in a specific tone.
And traditionally, fine-tuning was incredibly expensive. If you want to update the behaviors of a 70 billion parameter model, you have to calculate the gradients and update all 70 billion weights.
Which requires almost as much VRAM as pre-training.
Right. A developer with a single consumer GPU cannot do that. So how do we fine-tune without the massive overhead?
We use a breakthrough technique called PE, Parameter Efficient Fine-Tuning, and the crown jewel of PFF right now is LoRa, or low-rank adaptation.
LoRa. Okay, how does that work?
The math behind LoRa is incredibly elegant. Let's visualize the architecture. Inside those transformer blocks, you have massive weight matrices.
Okay.
Let's isolate one single matrix inside one attention layer of a large model. That matrix might be 12,288 rows by 12,288 columns.
Okay, let me do the math. Multiplying that out, that is over 150 million individual parameters just in that one single matrix.
And there are dozens of these matrices in every single layer of the network.
Wow. And loading those 150 million parameters into GPU memory, calculating their gradients during backpropagation, and updating them requires immense resources.
LoRa bypasses this entirely. First, it takes that original massive 150 million parameter matrix and completely freezes it. It locks it into read-only memory. Those weights will never change.
Okay, so the base knowledge is preserved and locked.
Then, LoRa injects a bypass route alongside that frozen matrix. It approximates the changes that would have been made to the giant matrix by introducing two new, vastly smaller matrices.
How much smaller?
Well, this relies on the mathematical concept of rank decomposition. Instead of a 12,288 by 12,288 matrix, LoRa might introduce matrix A, which is 12,288 by 8, and matrix B, which is 8 by 12,288. That number 8 is the rank.
Let me run that math real quick. 12,288 times 8 is roughly 98,000. So both of those matrices combined are under 200,000 parameters.
Exactly.
Wait, you are replacing the need to update 150 million parameters with updating just 200,000 parameters. You're reducing the trainable parameter count by a factor of nearly 1,000.
Often much more than that. And because you are only actively training 200,000 parameters, the optimizer states and gradients take up virtually no memory. You can run this fine-tuning loop on a standard consumer gaming GPU.
That's crazy.
So when you feed data into the model, the input passes through the massive frozen matrix while simultaneously passing through your tiny LoRa bypass. The outputs are then added together.
But mechanically, how does that not ruin the model? If the task is complex, like teaching the model a dense medical vocabulary or highly specific formatting, how can a tiny 200,000 parameter bypass possibly capture the nuance that would normally be spread across 150 million parameters?
Because of a concept called intrinsic dimensionality, the theory is that while language models require vast overparameterization to learn the incredibly complex high-dimensional structure of general human knowledge during pre-training, the actual adaptation to a specific new task exists in a much lower dimensional space.
Oh, I love the analogy we were batting around earlier for this.
The logistics one.
Yeah. It's like hiring a highly educated generalist. You bring in someone with a PhD in astrophysics, history, and literature. That person is your massive frozen base model.
Right.
When they start their first day at your logistics company, you don't send them back to kindergarten to rebuild their entire brain from scratch to learn your filing system. That would be full fine-tuning.
Which is a waste of time and money.
Exactly. Instead, you just hand them a 10-page specialized instruction manual on their desk. They retain all their vast general intelligence, but they now apply it strictly through the lens of that 10-page manual. LoRa is that instruction manual.
It is a perfect mapping of the concept. And the operational brilliance of LoRa is that those matrices are highly portable. When you finish fine-tuning, the LoRa adapter is just a tiny file, maybe a few dozen megabytes.
So you can swap them in and out instantly.
Exactly. A single base model on your machine can be an expert Python coder 1 minute, and with a hot swap of the LoRa adapter, a medical diagnostic assistant the next.
Okay, so LoRa solves the training bottleneck. We can fine-tune cheaply. But we still have a massive inference bottleneck.
Right, running the thing.
Yeah. Even if the base model is frozen, you still have to load it into RAM to use it. A 70 billion parameter model at standard 16-bit precision is a 130 gigabyte file. It requires multiple high-end GPUs just to sit idle in memory.
It's heavy.
What if we want to rip this technology entirely out of the data center? What if we want to run AI on edge devices, smartphones, microcontrollers, standard CPUs?
This brings us to the actual compression of the neural network itself. How do we shrink the giant down to a small language model, or an SLM?
Right, this is the most aggressive frontier of the engineering right now, isn't it?
It really is. We are realizing that for 90% of practical applications, a massive foundation model is extreme overkill. You do not need a 100 billion parameter model with a deep understanding of 18th century poetry if its only job is to parse error logs in an industrial sensor.
Or act as a smart TV remote.
Exactly. We're seeing incredibly powerful SLMs like Microsoft's Phi 2 at just 2.7 billion parameters or the Mistral 7B architectures.
And they get that small through 3 specific mathematical compression techniques, right? Knowledge distillation, pruning, and quantization.
Those are the big 3.
Let's go deep on these. Let's start with knowledge distillation. How do you distill a model?
Knowledge distillation fundamentally relies on a teacher-student dynamic. You take your massive, highly capable model, let's say a 100 billion parameter model, that is the teacher.
Oh,
You want to train a 2 billion parameter student model. If you just train the student on raw internet data, it would fail. The network isn't deep enough to find the patterns and the noise.
so you use the teacher to generate the curriculum.
Exactly. But it goes deeper than just generating clean text. You train the student on the teacher's logits.
Logits, what are those?
When the teacher analyzes a prompt, it outputs a probability distribution across the entire vocabulary. It doesn't just say the answer is apple. It says apple is 80%, fruit is 15%, car is 0.0001%.
Oh, I see.
That probability distribution contains what researchers call the dark knowledge of the teacher's internal reasoning. It maps the semantic relationships between concepts.
Oh, wow. So instead of the student model just being penalized for not guessing the exact right word, it's being evaluated on how closely its internal probability distribution matches the teacher's distribution.
Exactly. It's learning the shape of the teacher's logic.
This is Kullback-Leibler divergence, right?
Yeah.
Minimizing the difference between 2 probability distributions.
Yes, that is the exact mathematical function at play. Because the student is learning from these soft targets rather than the hard, messy reality of the internet, it converges on a highly capable internal representation with a fraction of the parameters.
Fascinating. So that's distillation. The second technique is pruning, which, well, it sounds incredibly destructive. You are literally deleting parts of the model's brain.
You are severing the connections, yes. Pruning algorithms analyze the neural network to identify weights that contribute the least to the final output.
How do they know which ones are useless?
Think of the model's learning objective as a topographic map, a loss landscape. You are trying to find the lowest valley of error. Pruning algorithms, like the sparse GPT method, calculate the gradient impact of every individual weight.
Okay.
They find the parameters where the gradient is flat, meaning that if you force that parameter to exactly 0, it doesn't push the model up a hill into higher error.
It has no impact on the final calculation.
Right. And because these massive models are vastly over-parameterized during pre-training, there is a massive amount of redundancy. You can systematically locate these low-impact weights and force them to 0. This creates a sparse matrix.
And when a computer multiplies a number by 0, the hardware can essentially skip the calculation entirely, vastly speeding up the processing time.
Precisely.
I've read that you can prune up to 60% of a model's connections without a noticeable drop in its core competency. You are basically just trimming the dead wood.
Trimming the fat, yeah.
Okay, the third technique, and probably the most common one an independent developer will use daily, is quantization. Let's break down the math of quantization.
Quantization attacks the memory footprint directly by reducing the mathematical precision of the parameters themselves.
How does that work?
Well, during training, a model typically stores its weights as 16-bit or 32-bit floating point numbers. These are highly precise numbers with long decimal tails. Storing 70 billion 16-bit numbers takes up an immense amount of physical RAM.
So you crush the precision down. You move from 16-bit down to 8-bit, or even 4-bit integers.
Exactly.
Think of it like image compression for you listeners. A 16-bit weight is like a massive, uncompressed 4K photograph. It has millions of perfectly distinct color gradients.
Right.
Quantizing that weight down to a 4-bit integer is like saving that massive photo as a low-res GIF. You lose the extreme nuance of the shading, the gradient isn't as smooth, but you can still immediately recognize that it's a picture of a dog. And the file size drops by 75%.
That is a highly accurate visualization of the mechanism. But the danger of quantization is the outlier weights.
What are outlier weights?
In any neural network, there are a handful of weights that are vastly more important than the others. They act as massive activation gateways. If you quantize those salient weights blindly, the model's intelligence collapses entirely. The GIF becomes so pixelated it's unrecognizable.
So how do you protect those outliers?
Through algorithms like AWQ or activation-aware weight quantization. Instead of just looking at the size of the weights, AWQ observes the model while a small batch of data runs through it.
Ooh, clever.
It measures which weights actually trigger the largest activations in the hidden states. It identifies the critical load-bearing columns of the network, and it keeps those specific rates at higher precision while aggressively quantizing the rest of the matrix.
And the result?
The result is a model that takes up a quarter of the VRAM and generates text much faster, because standard integer math is computationally cheaper than floating point math.
So we use distillation to shrink the architecture, we prune the redundant connections, and we quantize the remaining math down to 4-bit integers.
That's the recipe.
We have successfully taken a 130 gigabyte Leviathan and crushed it down into a 3 gigabyte file that runs at 40 tokens a second on a standard laptop CPU. This is the era of TinyML. We are talking about edge deployment.
And edge deployment fundamentally changes the utility of AI. We are moving computation away from centralized cloud servers and pushing it directly onto microcontrollers, FPGAs, and embedded systems.
Like incredibly small devices.
Right. Frameworks like MCUNet or Flight LLM are designed to run these quantized models on devices with single-digit megabytes of memory and severe power constraints.
We're putting a tiny localized brain into everything. A smart microwave that actually processes complex natural language locally to determine cooking times.
Or industrial sensors on a factory floor that can parse their own error logs and alert a technician in plain English.
Autonomous drones navigating complex environments without any internet connection. But I have to ask the obvious question. We have fast 5G everywhere.
Sure.
Why go to all this extreme mathematical effort to compress these models when we could just put a Wi-Fi chip in the microwave and have it ping a giant 100 billion parameter model in the cloud via an API?
Because relying on the cloud introduces 4 fatal bottlenecks for real-world deployment. The first is latency.
Oh, right.
If you are a self-driving car processing LiDAR data to determine if a shadow is a pedestrian, you cannot wait 250 milliseconds for a round-trip API call to a server in Virginia. You need deterministic, zero-latency inference. The computation must happen locally on the chassis.
That makes total sense. Physics demands local compute.
Second is bandwidth conservation. Imagine an industrial setting with 10,000 sensors. If every single sensor is continuously streaming raw telemetry data to a central cloud server to be analyzed by an LLM, the network bandwidth would instantly collapse.
Edge AI allows the sensor to process the data locally, and it only pings the network if there is a critical anomaly.
Exactly. Third is offline capability. A search and rescue drone needs to use computer vision and local reasoning to identify a missing person even when it's deep in a ravine with zero cellular service.
And fourth, and honestly the most important for consumer adoption, is absolute data privacy.
Yeah, privacy's huge.
If I have an AI-powered microphone in my kitchen or a smart camera in my living room, I absolutely refuse to have it streaming raw, unencrypted audio and video to a corporate server to be processed.
Right. No one wants that.
If the model runs entirely on the edge, on the silicon inside the device itself, my data physically never leaves my house. The privacy isn't just a promise in a terms of service agreement. It is mathematically guaranteed by the hardware constraints.
That's the real selling point for Edge AI.
Okay, I am entirely sold on the utility of the edge, but I have to push back on the capability.
Let's hear it.
If we aggressively prune 60% of the network, quantize the math down to 4-bit precision, and distill the parameters down to 2 billion, haven't we essentially lobotomized the model? I mean, I've run some of these tiny models. If you ask them a complex logic puzzle, they hallucinate wildly or loop into nonsense. They simply do not have the reasoning depth of the massive cloud models.
You have correctly identified the structural trade-off. We have to look at the mechanics of shallow networks. Research clearly shows that models with fewer transformer layers, shallow depth excel at grammar, syntax, and basic fact retrieval, but they fail structurally at long-term coherence and zero-shot reasoning.
Because they lack depth.
Right. Without a massive hidden state dimension, the model simply doesn't have the internal working memory to juggle multiple complex constraints over a long output.
So they are lobotomized generalists.
Yes, they lose their broad flexibility. They will
Sure.
never write a coherent novel or solve novel physics equations. But, and this is the foundational insight of edge deployment, an SLM becomes incredibly potent when you sacrifice generalization for hyper-specialization.
Give me an example.
Think about the smart TV remote AI. It doesn't need a 100 billion parameter network. It doesn't need to know how to code in Rust or explain the French Revolution.
It just needs to know Netflix.
Exactly. It only needs to understand entertainment commands, media genres, and schedule formatting. If you take a quantized 2 billion parameter model and use LoRa to fine-tune it exhaustively on thousands of variations of TV navigation intents, it will perform that singular task with the exact same accuracy as the giant cloud model, but it will do it instantly, locally, and privately.
Generalization is a luxury. Specialization is efficient. I love that framework. We take the generalist, we shrink it, we give it a singular focus.
That's the playbook.
This leads us perfectly into the final and arguably most important segment of our deep dive. We've established the mechanics. We know how the models are built, fine-tuned, compressed, and deployed.
The full stack.
Yeah. How do you, the developer listening to this, actually use these components to build something that elevates humanity? How do we use specialized AI as a tool for human augmentation rather than human replacement?
To achieve that, we have to move entirely away from the paradigm of the LLM as a chatbot. A chatbot is a passive entity. It waits for a prompt, spits out text, and goes dormant.
So what's the alternative?
The architectural shift that changes the game is the move toward agentic workflows. We are giving the LLM an orchestration framework that allows for a brain, perception, and action loop.
Walk me through that loop. How does an LLM take an action? It's trapped inside its neural weights.
It breaks out of the box using orchestration libraries like LangChain. LangChain allows you to tether the LLM to external tools. You give the LLM an API to browse the live web, a connection to a SQL database, or a Python read-evil print loop, our REPL environment.
So it has hands now.
Exactly. The LLM acts purely as the central reasoning engine. Let's look at the mechanical loop. The user inputs a complex request. The LLM's first step is to generate a thought. It breaks the problem down into sequential steps.
Okay.
Then it generates an action. It outputs a highly formatted string, like a JSON object, that LangChain intercepts. LangChain reads that JSON, executes the external tool, say, running a Python script, and captures the result. That result becomes the observation, which is fed back into the LLM's context window.
So the model might write a script to scrape a data set, execute the script, read a syntax error in the observation, think to itself, I forgot to import the math library, rewrite the script, execute it again, and finally get the data. It is iterating autonomously.
Exactly. It uses its internal logic capabilities to wield external tools. And this brings us to the core philosophical tension of AI development, the chess problem.
Yes, the chess problem. Decades ago, teaching a computer to beat a human grandmaster at chess was the holy grail of artificial intelligence. It was the ultimate test of cognitive capability.
And then Deep Blue beat Kasparov.
And later, AlphaZero completely solved the game using self-play. And what was the result? Playing chess directly against an unhandicapped AI is a miserable experience. It isn't fun.
No, it just destroys you.
The AI simply crushes you with cold mathematical precision. It makes the human player feel entirely useless. If we build agentic workflows that simply execute tasks perfectly from start to finish without any human intervention, we risk recreating the chess problem across the entire economy.
We end up building autonomous replacements that render human creativity and decision-making obsolete.
Right.
Which is exactly why the developer community must intentionally design architectures that force human collaboration. The technical mechanism for achieving this is combining specialized, localized small language models with RAG, retrieval-augmented generation.
RAG is the most vital architectural pattern in AI right now. We have to dive deep into how RAG mechanically works because it solves the hallucination problem and forces the AI to rely on human ground truth. How does RAG actually operate?
To understand RAG, you have to understand vector embeddings. When you want an AI to access a private data set, say a company's internal engineering wiki, or thousands of pages of medical research, you don't fine-tune the model on those documents.
Because fine-tuning is for teaching behavior, not memorizing facts.
Exactly. Instead, you chunk those documents into small paragraphs.
Yeah.
You pass each paragraph through an embedding model, which mathematically translates the text into a dense vector, an array of, say, 1,536 floating point numbers.
So it turns text into coordinates.
Yes. That array represents the semantic meaning of the paragraph as a specific coordinate in a 1,536-dimensional space. Concepts that are similar are grouped closer together in that geometric space. You store all these coordinates in a vector database.
Okay, so the entire library of human knowledge is mapped out as coordinates in a massive geometric space. What happens when the user asks a question?
The orchestration layer takes the user's question and embeds it into its own vector coordinate. Then it queries the vector database and performs a simple mathematical operation, usually cosine similarity, to find the exact text chunks whose coordinates are closest to the user's question.
Oh, that's incredibly efficient.
It retrieves those highly relevant, fact-checked human documents and injects them directly into the LLM's prompt window, along with the user's question. The prompt to the LLM essentially says, "You are an expert assistant. Answer the user's question using only the provided text chunks."
It's an open book test. You are artificially restricting the LLM's massive, hallucination-prone internal memory and forcing its reasoning engine to act strictly upon verified, retrieved data.
Precisely. This allows developers to build hyper-competent, domain-specific agents. Look at the ChemCrow architecture highlighted in the literature. It isn't just an LLM that read some chemistry books.
It's an agentic workflow tethered via RLE to verified molecular databases, safety protocols, and actual chemical synthesis tools.
Exactly. But the critical component is that it operates as a model as a service within a human-in-the-loop paradigm.
How does the human stay in the loop if the AI is doing the synthesis?
The AI acts as the cognitive exoskeleton. Consider the sheer volume of data in scientific research. A human researcher physically cannot read 10,000 new papers a month, extract the vector embeddings, and find a subtle multidisciplinary correlation.
Obviously not.
The AI agent handles the immense friction of data processing. It retrieves the patterns, tests the initial hypotheses against the safety constraints, and synthesizes a set of viable pathways. But the human exercises the faculties the AI mathematically lacks: high-level creative intuition, ethical judgment, common sense, and the ultimate strategic decision-making.
The AI does the heavy lifting of navigating the data space. The human steers the ship.
Right.
Let's map that back to the chess analogy. If you are a developer, your goal shouldn't be to build AlphaZero to beat your user. Your goal is to build an AI agent that acts as the user's ultimate coach.
Yes, exactly.
Imagine an agent that ingests the last 10,000 chess games you personally played. It maps your moves against a vector database of grandmaster games. It doesn't play the game for you. Instead, it identifies the exact strategic blind spots you exhibit in the mid-game.
It retrieves puzzles specifically designed to break your bad habits.
Right. It uses its massive pattern recognition capability to explain the underlying geometry of the board to you. It makes you, the human, a more competitive, deeply understanding player. This is Centaur chess, the human-AI hybrid.
That is the highest calling of this technology. You are leveraging the deterministic mathematical pattern recognition of the neural network to elevate the biological, intuitive capability of the human user.
So if you are a lone developer listening right now, you stand at a massive crossroads. You have a profound architectural choice to make. You can build closed autonomous systems designed to sideline human involvement, mimicking the centralization of big tech. Or you can purposefully build collaborative exoskeletons.
And the existence of the democratization toolkit is what gives you the leverage to make that choice. If the technology remained entirely locked behind the $2 million compute barrier of the foundation models, massive corporations would dictate the architecture of human-AI interaction.
They would naturally drift towards centralized lockdown systems that maximize automated labor.
Exactly. But because you have access to open weights models on Hugging Face, because you understand how to use low-rank adaptation to fine-tune 150 million parameter matrices efficiently, and because you can utilize distillation, pruning, and quantization authorization to deploy these models onto local edge silicon via LangChain and Raji, you hold the power.
You can build highly customized, hyper-specialized, privacy-guaranteed agents that run directly on a user's local hardware.
You can build tools that preserve human agency and prevent a monopolistic bottleneck on artificial intelligence.
It is an incredibly empowering realization. We have completely stripped away the magic. Let's recap the mechanical journey we just took. We started by looking at the staggering scale of the foundation models.
The massive tensor parallel compute clusters required to optimize trillions of parameters.
Right, running autoregressive next token prediction across petabytes of TACT and Python code, forcing the network to build deep internal representations of logic.
We then explored how to bypass that massive barrier to entry using the open source ecosystem, digging into the matrix math of LoRa to achieve parameter-efficient fine-tuning on consumer hardware.
We looked at the aggressive compression algorithms required for edge deployment, using soft target knowledge distillation, navigating the loss landscape to prune redundant neural connections, and utilizing activation-aware weight quantization to crush the precision down to 4-bit integers.
All to deploy zero-latency, highly secure models onto local microcontrollers and smart devices.
And finally, we discussed the architecture of augmentation, moving from passive chatbots to agentic workflows, utilizing vector databases and RA to force human-grounded truth.
Keeping the human firmly in the loop to drive creative and strategic decision-making.
The black box is open, the toolkit is available, you have the mechanical knowledge to download a model today, fine-tune it locally, and build an architecture that enhances human capability in whatever specialized domain you choose.
It's all right there for the taking.
But before we wrap up this deep dive, there is one final paradigm-shifting concept from the research that we have to leave you with. We have spent this entire hour talking about mathematical hacks, compressing and manipulating software to force it to run efficiently on standard, traditional hardware.
But the physical hardware itself is about to change entirely.
Wait, really? How so?
The architectural shift on the horizon is going to render everything we just discussed obsolete. Currently, we operate on traditional von Neumann architecture, where the memory unit and the processing unit are physically separated by a bus.
Right, and moving data back and forth across that bus is the primary bottleneck in all AI computing.
Exactly. Researchers are aggressively developing processing in memory, or PM, which fuses computation directly into the memory cells. But the true frontier is neuromorphic silicon.
Neuromorphic chips. The research specifically highlights the Tianchik architecture. These chips abandon traditional digital computing entirely.
They aren't running tensor calculus across floating point numbers.
Right. They're designed to physically, structurally mimic the continuous spiking neural networks of a biological brain.
They process information through asynchronous physical spikes, integrating memory and computation at the exact node level, drastically reducing power consumption while increasing parallel throughput organically.
So they are silicon structures fundamentally aligned with the true nature of neural processing. So as a developer, imagine what you will be able to build in a few years, when the physical hardware itself processes information exactly like a human nervous system, when we no longer have to simulate a neural network using floating point math, but actually grow one in silicon.
It changes everything.
Suddenly, that algorithmic engine we've been looking at under the hood stops looking like a machine and starts looking vastly more organic, something to mull over until our next deep dive.